Hello and welcome to part 9 of the book summary. Today, we are going to be covering real-time clock, RTC, and multitasking tools such as mutexes and task notifications provided by FreeRTOS. RTC is an external peripheral which you can use to accurately keep track of time in your projects. Most of your electronic devices, like computers or phones, have this inside them, and luckily, the Blue Pill has a built-in RTC tool that we can use. With this peripheral, we can configure interrupts to trigger at every specific intervals, such as to trigger every second. This is a change of pace, but now I'm going to show you this chapter's demo, which is a simple USB serial terminal timer where it prints out the time every second. And also, you can press A to set an alarm to trigger 10 seconds later. Alright, I'm going to plug the USB connected Blue Pill into my laptop. Now, let's open up Miniterm. And it is showing up here as device 1. Press 1 to open serial communication. And then there's this weird bug that causes some erratic serial printing behavior. But worry not, after a while it'll be fine after the timer has overflown. Okay, now that the serial terminal is behaving normally, we could see here that if we press A, it will set an alarm to trigger 10 seconds later. So let's try it now. Press A. Alright, now that the timer is being set, let's wait for a while. Nice, the alarm triggered 10 seconds later and the time is printed out too. So let's just set another alarm for good measure and wait another 10 seconds. And as you can see, it printed out the time 10 seconds later, and everything is working as intended. Now, let's take a look at the sample code given. Here's an overview of the code. There are 3 main tasks. Task 1, which is a terminal console that waits for an input from the user. Task 2, which prints the time and is a tick interrupt task. Task 3, which is an alarm interrupt task. In the best case scenario, interrupts should be as short as possible so that it doesn't block another interrupt from occurring. Thus, codes that are CPU intensive are done separately in the normal task routine, away from the interrupt routine. One good example is the printing of characters to the USB serial console. Here's a more graphical overview of the code. So we got our task and our alarm interrupts. The first task waits for an input from the user to set an alarm interrupt. Once the alarm is set and the interrupt alarm is called, it enables task 3, which prints out the alarm interrupt time. Then, for every tick interrupt, it wakes up and enables task 2, which just prints the time out and shows the number of interrupts that have occurred. Finally, in the case of a timer overflow, it updates the timer overflow variable in the interrupt routine itself, as it is a rather trivial task. Now, let's take a look at the code that relates to the RTC. So, over here we have the RTC setup function that configures the RTC that we are going to use. We specify RCCHSE to indicate that we are going to use the built-in clock source, which is around 625 MHz. Then, we set the prescale to 625,000, which results at a tick rate of 1 second. Also take note that the counter starts at a rather high value. This is done on purpose to trigger an overflow interrupt as shown earlier in the demo, even though it seems to be a bit buggy. And finally, on the last few lines, we enable the different interrupts: the tick interrupt, the alarm interrupt, and the timer overflow interrupt. Next, we take a look at the RTC ISI routine. This function is called at every interrupt routine. First, it determines what kind of interrupt it is. For example, if it's an overflow interrupt, it will execute this block of code, which basically just increases the number of interrupt count and clear the interrupt flag. If it is a tick interrupt, this block of code will run instead. Notice that it enters a critical section, meaning that the RTOS scheduler will not switch to other tasks while updating the timer variables, otherwise it will mess the timings up. It also wakes task 2 up. Finally, if we look at the alarm interrupt, it basically just wakes up task 3 using task notifications and increment the alarm count. So what are task notifications? They are simple task waking and sleeping mechanism, where a task can be programmed to wait for a notification from another task or an interrupt routine before executing its blocks of code. Here is briefly how to use them. Initialize the task handler variables, then assign them to the necessary tasks, and finally notify the task when needed. And then the task will execute the block of code when it is being notified. Then there are mutexes. It is similar to task notifications in which it helps us to determine which set of tasks to execute. But there are some differences in between them. Mainly the fact that a mutex handle is not task specific, meaning that any task could access this mutex variable or mutex handle. If we take a look at the two functions mutex lock and mutex unlock, as the name suggests, it acts more like a lock and key system, meaning a task will always try to take a mutex, and if the mutex is not available, the task will yield its computing time until it is available again. The mutex is usually returned at the end of the code with the mutex unlock function. Why is this needed? This is to prevent a race condition and competition of shared resources among multitasking tasks. Here's a graphical example. Suppose we have 3 tasks, which prints out sentences to the serial console. Initially, the task scheduler allocates computing time to task 1 to print out a sentence to the console. But before it can finish, the task scheduler switches to task 2. And while task 2 is still printing out a sentence, the task scheduler switches to task 3. As you can see on the serial console, none of the tasks manage to print out a complete sentence. This is a rather extreme example, but we get the idea here. So, to fix this, let's use mutexes. Let's repeat the example again. This time around, task 1 will take the mutex before printing to the console. Now, let's assume that the same thing happened again, in which the task scheduler switches to task 2 before task 1 is able to completely print out the sentence. Task 2 tries to take the mutex, and it realizes that the mutex is missing. Thus, it yields its computing time and does not print anything at all to the console. The same thing happens as the task scheduler switches to task 3. Task 3 again, like task 2, checks for the mutex and realizes that it is not available. Thus, it also yields its computing time. Finally, when the task scheduler switches back to task 1 will finish printing a sentence and give the mutex back. Next, when the scheduler switches to task 2 takes the mutex and thus is able to run and print out a sentence to the serial console. This is how it is pretty much implemented in the demos. Before every serial print, you can see the mutex lock function and the mutex unlock after the print, which is shown here in task 3 itself. I believe we have gone through quite a bit for this video. And now it's time for the summary. Here's a list of what we basically went through in this video. Here are some references for further readings if you are interested, and if you want to find out more about RTOS mutexes or the RTC peripheral itself. With that, I'll at the end of the video here. Thank you, and keep on learning. Bye bye.